Okay, in this lecture, we're going to talk about radical expressions. Now, or review of radical expressions. Now, if you recall, radical expressions are expressions that are in this form, where here we have the radical symbol, right? This is called the radical symbol. N is the index of the radical. The index has to be 2, 3, 4, and so on, natural numbers or integers greater than or equal to 2. And here we have algebraic expression, which we call the radicand. So this would be the anatomy of the radical expressions for us. So we're going to take a look at these radical expressions now. Now, previously, we used rational exponents to express roots, right? So, for example, if I have something that's like 2 to 2/3, the question is, how can I rewrite this rational exponent? Remember, rational means fractional exponent. The question is, how can I understand? How can I rewrite this? So, in order to do this, we need to look at the relationship between fractional exponents and radicals. And the relationship in general is stated in this form. If you have any number to a rational exponent in m over n, we can write this as the nth root of a to the m power and the nth root of a, the whole thing to the mth power, right? Now, I assume everyone is familiar with just basic work with radicals. So, for example, when we say square root of 25, we're talking in number. A number times itself results in 25. So the answer is 5. Every radical expression has an index. If the index is 2, and remember, index has to be 2, 3, 4, and so on. If the index is 2, we call that square roots, and we don't typically write it. So instead of writing, for example, square root of 9 like that, we simply write it as, as 9 like that. Now, by definition of a square root, so for example, square root of 25, square root of 25. That means a number squared becomes 25. Well, 5 squared is 25. So is negative 5 squared, right? Now we are interested in positive answers. Okay, and indeed, the square root symbol represents the positive, or we'll call it a principal root. Positive root. We know that the negative root works, but in our work we're interested only in principal or positive root. So instead of saying that we are interested in positive roots, we simply use the symbol. So if the symbol says 64 here, we know that the answer is going to be 8, although negative 8 square works, right? But we use the square root. That means principal root or positive root. So real quick, just a review of radicals. Now the higher roots work the same way. So for example, cube root of 8, that means a number times itself, this time 3 times. That gives you the radicand. 2 is the answer. Now in case of cube roots and in general odd roots, then radicand may be negative, because it is possible to multiply a number, odd number of times, negative number, and the answer will be negative. In the case of square roots, if we have a negative root, we said that this is not real, because it is impossible to get a number times itself, a real number times itself. See, negative 8 times negative 8 is a positive 64, and of course 8 times 8 is also positive. So regardless of whether the number is positive or negative, the product is always positive. So for that reason, we don't allow negative in the radicand of square roots, and in general even roots. So square root, 4th root, 6th root, and so on. For all of these, the radicand must be positive. Radicand has to be greater than or equal to 0. which implies the number must be positive. Or if it's a variable, the variable has to be positive. But we don't have restriction on odd indices. Okay, the odd index. Now, let's take a look at, so this is the key relationship that connects rational exponents and radicals together. So using this notation, now I can rewrite at least 2 to 2/3 using radical notation. A is 2. Index, which is the denominator, n, is 3. So I'm looking at cube root of 2 squared. That would be cube root of 4. And we're going to leave it like that. And the reason is because I cannot think of, we can guess, but not exactly. I cannot think of a number times itself that 3 times that becomes 4. I know the answer is not 2, because 2 by 2 by 2 is 8. So the answer is going to be less than 2, but greater than 1. Usually for these we use a calculator if we need to. So if the cube root, if the radicand is not perfect cube, perfect cubes are, let's say, 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and so on. So if I have cube root of, for example, 64, that answer is going to be a whole number, right? A natural number. So any number other than these perfect cubes, their cube root is going to be irrational. So we can maybe, we'll point to this out later on as we need them. Alrighty, so what are we gonna do here? Let's take a look at another example. What if I have, for instance, negative 16 to 3/4? What does this number mean? Again, negative is on the outside. If it's on the outside, not in parentheses, and we're not going to include it in the radical. So it's going to be negative. In other words, just look at 16 to 3/4. That's going to be the 4th root of 16. Then you can put the cube on the outside. You could also go, you can go the 4th root of 16 cubes, right? 16 cubed. Now, I don't want to do 16 cubed. That's going to be a large number. So it's better to just go with 4th root of 16, that result cubed. Now, the 4th root of 16 is 2, because 2 times 2 times 2 times 2 is 16. And you cube that. 2 cubed is 8. And notice the negative stays outside the whole time. So this answer is going to be negative 8. All right. Now, if the number was in parentheses, it would have a whole different meaning, wouldn't it? Look at this one, negative 16 to 3/4. Now, that's going to be the 4th root of negative 16 cubed, right? And this time, because the radicand index is even, radicand cannot be negative, so this is not real. Means I cannot think of a real number times itself 4 times, that becomes negative. Okay. And so that's how we convert from one to another form. Now, in evaluating, by the way, the nth root of expressions, the nth root of a to the n in general is going to be absolute value of a, okay, if n is even. And the reason is because what I mentioned earlier here. The radical symbol implies principal or positive root. So the insertion of absolute value here guarantees the result is positive. Okay, what if n is odd? If n is odd, and I had an example, the index is odd. I had the example here. So if the index is odd, then there is no restriction on the radicand. So the nth root of a to the n is simply a to the n. It can be negative, the answer, and that's not a problem if n is odd. So this is something noteworthy, something we're going to keep in mind. Therefore, let's take a look at, for example, suppose I have cube root of k cubed. So cube root of k cubed, because index is odd, so that's just going to be k. Although I don't know what k is. K could be negative. And if k is negative, that is perfectly fine because cube roots may be negative. In other words, there's no need for absolute value. What if I have the fourth root of x to the fourth and I don't know what x is? Well, if I just write this x, there is a potential that x could be negative, right? So for this one, I do need to put absolute value. X could be negative 4, but then remember the radical symbol means we want positive answers. And there you have that one. What if I have an expression like this? Suppose I have the fourth root of negative 2 to the fourth power. Now, for this one, I can do it a couple of ways. Using the property, this is going to be absolute value of negative 2, which is 2, because the answer index is 4. The answer has to be positive. Or, without using absolute value, well, negative 2 to the 4th is 16. The fourth root of 16 is 2. So either way would work. What if I have something like this one? Suppose I have square root of x squared minus 4x plus 4. How are we going to work this one? And for this one now, because we cannot take individual roots. So for example, if I have a squared plus b squared plus c squared, I cannot say that's a plus b plus c. Individual roots we cannot do with addition, subtraction in the radicand. Now, had this been a squared, b squared, c squared, then I can do that, right? Then I can say the answer is going to be absolute value of ABC. There. But it's not a product in this example. We have sum and difference. So what I could do, I could factor. If this isn't factorable, by the way, there's nothing I can do. Just look at it. Not much. But this is factorable, and the factored form I can see is x minus 2x minus 2. That gives me the 4. The sum gives me negative 4. Yeah, that should work. And now we can rewrite this as a square root of x minus 2 quantity squared. And the answer is x minus 2. Now, again, as long as the answer has potential to be negative, which this one certainly does. For example, if x is 0, see, the answer is negative. But the sign, the radical sign, means positive or principal root. Therefore, we need to put absolute value here. And we need to maintain the absolute value on the binomial. We cannot say that's absolute value of x minus absolute value of 2. It doesn't work. In the case of a product, we can write as absolute value of a product would be product of absolute values, but sum difference, absolute value of sum difference is not going to be a sum difference of absolute values. Okay, now we do have some rules of radicals here. I want to recall some of the rules we had. For example, the product rule of radical, the nth root of a, nth root of b, is going to be simply the nth root of ab. Now, here we got to be careful, okay? Because not always these product rules are valid. What makes these valid is that a and b are real numbers here, okay? And n in this case has to be a positive integer for which the roots are real. So what do I mean by that? Let's say I'm doing square root of 5 times the square root of negative 1. Now let's say, there you go, negative 5, not 5. Notice this is not a real answer, right? Square root of negative 5 is not real because the radicand is negative. And neither is this one. So the product rule does not apply. I cannot say that's negative 5 times negative 1, and the answer is not going to be 5. Okay, so these nth root, the nth root of a, nth root of b, at least one of them at least one of them has to be real. Okay, now if that is the case, then we can use, this is called the product rule of radicals. Okay, and then we have the division, or as we call it, the quotient rule of radicals. The quotient rule of radicals allow us to write the nth root of a fraction as nth root of a over nth root of b. And remember, the same restriction works with quotients, so I cannot do square root of -5 over square root of -2 and say that's square root of -5 over -2 and magically it becomes positive. We are not allowed to do this. Okay, but if one of them is actually, then we could. And in other words, at least one of these roots must be positive, a real number. Okay, so there's the quotient rule. Now, what about the power rule? So for the power rule, we're going to have the mth root of a. This we can write it as the mn root of a. So simply multiply the indices together. And this one is not that often used because again, in our work, if need be, we have it, because as much as possible we try to keep the radicands the same in our work. So in other words, we work with just square roots, cube roots, and something like that. We don't mix them usually, unless the exercise wants us to practice with that. Okay, so let's take a look at some examples here. Now, let's say I have something like square root of 175. Okay, and we want to simplify this one. Notice 175 is not a perfect square number. Okay, in other words, a number square cannot be 175. I can't think of one. The closest one is 169, right? Which is 13 squared. So this is just above 13. Now, in this case, what we need to do is we need to simplify this. And the way to simplify is to use the multiplication rule of radicals. I can break 175 as product of 25 times 7. And then use the product rule here to break the radical into product of two radicals. Root 25 times root 7. Square root of 25, of course, is 5, and 7 stays in the radicand. So that would be the answer to this one. Okay, the product rule. So this is what we call radical in a simplest form. So I guess, what does it mean for radical to be simplified? For radical to be simplified, that means the radicand has no factor that is raised to a power that is greater than or equal to the index. So this is what I mean. 25, I can write it as 5 squared. So I mentioned again, the radicand, which is 5 squared. It has no factor raised to a power, here factor 5. It is raised to a power that is equal to the index. So when that is the case, then the radical is not in simplest form. But square root of 7, look at that one. Index 2, the power on 7 is 1. So this time, truly, this factor 7 is not raised to a power that is equal to or greater than 2. 1 is less. So we can't do anything with 7. Also, the radicand cannot have a fraction. So if I have a square root of 2/3, that's not a radical in simplest form. We have to split it into two radicals. And also, denominators cannot contain a radical. Okay, so that means the square root of 3 isn't even allowed in the denominator. So it's going to be root 2 over root 3. And the way to get out of the square root of 3 in the denominator is to multiply top bottom by square root of 3. Root 3 is root 9, which becomes 3. See, that's how we can get it out of the radical in the denominator. In the numerator, 2 times 3, they're both positive, so we can use multiplication rule. And now that is the radical in simplest form. So remember, denominators cannot contain fractions. Now, the exponents in the radicand again and the index of radical must have a GCF of 1. Okay. So, which is pretty much what I mentioned earlier. That goes back to no factor raised to a power that is greater or equal to the index. Okay. So again, look at 7. The exponent on 7 is 1, index 2. What's the GCF of 1 and 2? 1. So the exponent in the radicand and the index have a GCF of 1 in this case. That one is seldom mentioned, but that's there also. All right. So let me write these for you so you have them. And there you go. I just wrote this down. So a radical is said to be in simplified form if 3 things. The radicand has no factor raised to a power greater than or equal to the index of the radical. The radicand has no fractions, and no denominator contains the radical. Then we say the radical is in simplest form or reduced form. So let's do some example of this now. Suppose I want to simplify in this example. Let's say I want to simplify the 6th root of 3 squared. Now 6th root of 3 squared, that's going to be well, that's the 6th root of 9, right? So one way I can do this is to go to the rational exponent form, and 2 6 is 1/3, and then go back to radical form. Yeah, isn't that cool? So we were able to reduce it. Let's say I want to do something like this. What about I have the 6th root of x to the 12th and then y to the 3rd? Okay, so again, I can write this as x to the 12th, y to the 3rd, to 1/6 exponent using the power rule of radicals. We rewrote it as a rational exponent. And then the power rule of exponents, I can write this as x to the 12th to 1/6 raised to 1/6 times y cubed raised to 1/6 power also. Now 12 times 1/6, that's going to be 2, right? We're multiplying the powers here. 12 times y 1/6 is 2, and 3 times 1/6 is 1/2. And that's going to be, oops, that was y. So it's going to be x squared y to a half. Now, because we're given a radical, we're going to write the answer in radical form. So I'm going to go back, instead of square root of y to a half as a rational exponent, fractional exponent, we can write it as the square root of y. And there is the answer to that one. Okay. What if I have, let's see how we can add and subtract. How's that? Add and subtracting radicals. So we're looking at addition / subtraction of radicals now. Now, in order for radicals to add or subtract, they need to be like radicals. Okay, like radicals are like terms. They look identical. The radicals look exactly the same. So for example, let's say I have the 4th root of 11mn negative 7th times the 4th root of 11mn. See how they have to be identical to be like radicals. So we got one of that, negative 7 of the same. The answer is going to be negative 6, 4th root of 11mn. the radicals, on the radical side, they have to be carbon copy of each other, identical for them to be combined. Now, what if they're not like radicals to begin with? If they're not, we may be able to actually rewrite them, simplify them, and then hopefully they become like radicals. So let's say I want to do example of a cube root here. Suppose I have cube root of 64 m fourth n fifth. And then I want to subtract cube root of negative 27 m 10 n 14th. Okay, suppose I want to do those. I want to subtract them. Well, first I need to factor each of these, right? So because it's cube root, because this is cube root, I'm going to write this as 64 m cubed and n cubed. I still have an m. Actually, let me use a different color here, because that's going to really help clarify what we're doing here. Perfect cubes. Okay, perfect cubes, I'm going to write them in red. Okay, 64 is a perfect cube, means I can take its cube root and it becomes 4. M cubed is perfect cubed, n cubed is perfect cubed. Okay, so I actually have the perfect cubes written in the first radical. Now I had m fourth, so I have one more m. I had 5 n's, I need 2 additional n's in the first radical. Now in the second radical, we're going to do the same thing. Okay, negative 27 m10 n 14th. We want perfect cubes now in this second one. Well, negative 27 is perfect cube. That's negative 3 times negative 3 times negative 3. And I can write this as m cubed, m cubed, m cubed. That I have 10 factors of m to work with. So those are 3, 3, that's 9. I still have 1 m outstanding. And on n, I'm going to go n cubed, n cubed, n cubed, n cubed. That will pick up 4 times 3, 12 factors of n, correct? And so I'm still going to have 1 m and 2 n's outstanding. Now for every perfect cube factor, we can write these outside the radical. Okay, therefore 64 outside the radical becomes 4, m cubed becomes n, m, n cubed becomes n. With the other radical, negative 27 becomes negative 3, and then I have 1, 2, 3 perfect cubes, m, m, m coming out. 1, 2, 3, 4 n cubes, n, 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 n. And I'll show you after I'm done with this one how we really do this, because if the exponents are large, we really don't want to do it this way, right? It just takes too much space and takes too long to do it. But this will illustrate what we're about to do and why it works. So let's write down what's left over. M n squared, and then I have minus, right? That's this minus. Remember the negative 3 here, that was the result of cube root of negative 27. So I still have the negative. That was from the problem was subtraction. And then we have cube root of mn squared. All right, and hopefully you're following what I'm doing. So I can write 4mn cube root of mn squared. Double negative here makes positive. 3m cubed n fourth times cube root of mn squared. Now we have like radicals. Okay, we have like radicals, so we can actually combine these. When we combine, here's 4mn, plus 3m cubed n fourth. We combine the coefficients times the common radical cube root of mn squared. All right, and there we have it. So that's how we can subtract radicals. And of course here we can get a GCF, right? So let's continue with this. I'm going to factor mn, the GCF. So it's going to be 4 plus 3m squared n cubed times cube root of mn squared. That's the final answer for this one. Now, again, doing this, we don't like doing that. There is actually an easier way to do this, where we don't have to list all perfect cube factors or perfect factors of the index. So let's take a look at, I'm just going to call that as a note. This is the final answer, but here's our note. Suppose I want to do cube root of m10 and 14. Remember, the answer was this, right, to the cube root. Let's see if we can get that a little faster. So the way to do this a little faster is to do long division of 10 divided by 3. The reason we do long division because we want to know how many whole factors, groups of size 3 are there in m to the 10th. So 3 times 3 is 9. Subtract, you get the remainder. This tells me this is quotient. And this tells me there are 3 groups of m cubes. You see that? 1, 2, 3. And if we do 14 divided by 3, how many groups of m cubes in 14? Well, 4 times 3 is 12. Subtract, we have 2. That's the remainder. This is the quotient. There are 4 whole groups of n cubed now. 1, 2, 3, 4. Okay, that's why that long division works, because we did it the longhand. Now we're doing it the shorthand. So at this point, this is how we're going to write this. We're going to put m and n on the outside, m and n on the inside. The quotient on m was 3. We're going to put that outside. Quotient on n was 4. We'll put that on n on the outside. And then we'll attach the remainders for the exponents on m and n. Exponent on m in the radicand has exponent 1. And exponent on n in the radicand is going to be 2. And there you have it. So we reduced it. And of course, m to the first is m. Now, if you look at this answer, they are the same. So typically, this is how we do it with larger powers of the exponent. Okay, we do the long division rather than breaking it off. And hopefully this will, help you work these higher powers in the radicand. So let's take a look at more examples here. Example, let's say I want to do 2 square root of 5. I'm going to multiply it by square root of 3, negative 3 root 6. So with this, we're going to distribute 2 square root of 5 times 3 is 15. 2 times 3 is 6. Square root of 5 by 6 would be 30. So that's going to be 2 root 15 minus 6 root 30. And that's as far as we can go. Even if I write this as product, there are no perfect squares in 15. 3 times 10 is 2 times 5. Yeah, there are no perfect square numbers in 30, so we cannot simplify them. That's as far as this will go. Okay. Let's try some other examples. Let's say I want to do cube root of 125. Now we want to evaluate this one. Again, cube root of 25 means a number times itself 3 times. 5 would be that number. So that cube root is 5. What if I want to do the fourth root of 81? Again, this time a number times itself 4 times. 1, 2, 3, 4 times. And looks like 3 is the answer. And what if I have negative, by the way, 125? This time in negative 5, negative 5, negative 5, that product is negative 125. So notice with odd index, it is possible to have negative radicand. Now, let's do something like rational exponent, m to 2/3. This one we can write it as cube root of m squared. Or we can also write it as cube root of m, the quantity squared. Remember, there are 2 versions of that according to our opening. Oops, sorry. Don't want to make you dizzy. According to this. All right. And let's take a look at another example. What if I have something like this one? Now suppose I have the 4th root of x to the 4th, and let's say x could be anything. Okay. The answer is going to be, you can rewrite it as a rational exponent. That's 4 over 4. Oh, which 4 is 4? Let me actually do this. Because they're identical 4s, we're going to make them distinguishable 4s. Suppose I have the red 4 that is exponent on x. The index is 4 also. So there you go. The exponent on x is actually going to be 4, and the denominator, the fraction, is the index, and that's just x. Now, because x again could be negative with even indices, we want positive roots. We do need absolute value here. That way, again, we are guaranteed the answer is positive. Now, if we are told, which we will be later on in the book, if x is positive, then the 4th root of x to the 4th is simply x, because x cannot be negative. There's no way that would be negative if this is a given. If it's not given, then we have to account for negative. All right, and we have that one. Next, let's take a look at something like a number square root of 72. We want to simplify this one. So how are we going to do it? Well, 72, we can think of 9 times 8, right? Square root of 9 is 3, square root of 8. Well, 8 itself is 4 times 2. So that would be square root of 4 is 2, and the answer is going to be 6 root 2. Now we can cut down in the number of steps. Had we recognized the greatest perfect square in number 72, and this is what I mean. The greatest perfect square in 72 is 36. 36 times 2, and 36, of course, square root of that is 6. So 6 root 2 is going to be the answer. Get the exact same results here. So when we try to reduce them, we always want the greatest perfect squares in this work. Let's see, what else? Let's do just maybe one more. Again, there's a lot more to these. What I'm doing is a review of all of these concepts. If you need to get more beyond what we're doing, you need to review an elementary, or actually radicals or intermediate algebra level, and review them in grade length. Okay. 8 root 2x negative square root of 8x plus square root of 72x. Let's say we want to combine these if we can. Now, if you look at this, there are no like radicals at this point. So I'm just going to rewrite the way they are. 8, I can write 8 as 4 times 2. 72, we can write that as 36 times 2. And then we can take the square roots. 8 square root of 2x, take the root of 4 on the outside is 2, and 2 square root of 2x. 36, that's going to be 6, and then root 2x there. Notice now we have like radicals. And when we do, we simply combine the coefficients. 8 minus 2 plus 6, and choose one common radical. So this is going to be 12. 8 minus 2, 6 plus 6, 12 rad 2x. And there you have it. Okay. And that's pretty much it. Let me make one last one here. And again, if we need to practice something about these throughout the course, I will recall some of these concepts. But let's say we want to do simplify 5/2. Now we don't want to use a calculator, so we don't want to say, I mean, it is 2.5, but that's not simplified, right? So we don't want to use calculator here. So what we do, remember, one of the rules of radical in simplest form is number 2. We said no radicand is allowed to have a fraction. Well, look at the radicand here. The radicand is indeed a fraction. So we need to split it into the numerator and the denominator. Now, square root of 2, again, notice this is an irrational number. Anytime we get the square root of non-perfect squares, the answer is going to be irrational. Irrational means you cannot write it as a ratio of 2 integers. So I'm going to multiply top bottom of this by square root of 2, because I'm not allowed to have a fraction. And then number 2 was you're not allowed to have a fraction. Number 3, no denominator. Oh, we cannot have a radicand in a fraction. That was number 2. And then number 3 said no denominator contains a radical. Well, look at the denominator. It has a radical. So we are not allowed that either. That's why I multiply top bottom by root 2. So on top I'm going to get 10. In the bottom, root 2 is root 4, which makes it 2. And now we have no radical. So we're good. We don't have a we have a fraction. We are not allowed a fraction in the radicand. That was the problem. But having fractions, there's nothing wrong with fractions. Now, notice also how square root of 2 is irrational. Now 2 is irrational. It means you can write it as ratio of 2 integers. 2 is integer, 1 is integer. Square root of 2, even if I write it as root 2 over 1, this one is fine, it is integer, but this is not integer. Therefore, that's irrational. And this process of turning something irrational into rational, you probably heard of that one. It's called rationalizing the denominator. So what we did indeed was rationalize the denominator. The denominator. Okay, and there we have it. How we rationalize denominators depends on the expression. So this, again, illustrated an example of it. Okay, well, I think we are good with this review. So hopefully you followed everything we did. Again, if you need to, please feel free to go back and watch the video again. But we're done with this review and this lecture again. Thank you for watching.